Welcome, ladies and gentlemen. May I have your attention, please? Thank you. So in order to determine where our original function y has horizontal tangents, what's our general strategy going to be? Jake?
When in doubt, just differentiate it. If you don't know what to do, maybe something will come to you after you differentiate the equation.
So unit 3 is all about derivatives, so differentiation is going to be a good bet. Well, maybe. It depends what we're trying to find, though, right? We're trying to find where the curve has horizontal tangents. So what would our differentiation help us do?
Find the horizontal tangent.
Find where the slope doesn't change. Zero.
We'll find where the slope is 0. Find where the slope is 0. And so given an original function y, its slope anywhere along it is given by its derivative y prime. And so we would use differentiation to generate a derivative function, call it y prime, and then see where that derivative function y prime is equal to 0. And so we've got our plan of attack. Let's go ahead and generate an expression y prime. So in order to do that, it looks like we'll differentiate. We can differentiate in accordance with the, product of powers. So we'll use product rule overall. And within the product rule, we'll use the power rule, right? So we can get our power wheels, power rule, jingle involved. And then we get to do the chain rule, right? Because each of these powers have bases that are composite functions, right? So let's go ahead and start. So the derivative of a product of two functions is the derivative of the first, and don't forget your chain rule. Exponent times the base raised to 1 less times the derivative of the base, right? Lots of people forgot that times the derivative of the base. What's the derivative of the base of the power function? 2. And so we need that 2 multiplier as the derivative of the base. Times the second function. So that is the 3x plus 4 to the 4th, as is. And then plus the first function. So that was my 2x minus 5 all to the 9th. Times the derivative of the second function. Now we get to use the power rule again with the chain. So exponent times the base raised to the 1 less times the derivative of the base. Don't forget that times the derivative of the base. This is a chain rule, right? So times the derivative of the base is a 3. And now how do we do? So we've got the 9, we've got the 2. Take a look at yours. Plus we've got a 4 here and the 3 here. Are we good? Okay, let's go ahead and simplify now so we can set this expression y prime equal to 0 and solve more easily. So we are going to take our expression y prime and set it equal to 0 to see where the slope is 0. That would indicate a horizontal tangent. But before I set this equal to 0 and solve, I think it would be useful to simplify. So let's go ahead and simplify this as much as we can. We've got a 9, we've got a 2, so our first term looks like a coefficient of 18, 2x minus 5 to the 8, 3x plus 4 to the 4th, plus, how do we do? Okay, second term, 4 times 3 is 12, quantity 2x minus 5 to the 9th times quantity 3x plus 4 to the 3rd, yes? Awesome. Now let's go ahead and see if we can continue simplifying, right? I know that if I set this equal to 0 and solve, the 0 product property would be useful because I could set each individual factor equal to 0 and solve separately. And right now I have a sum or difference. And so let's see if we can't factor this further. In other words, what's common to each of these terms in my overall sum and difference? Well, they all have 2x minus 5's in them. They all have 3x plus 4's in them, and they all have 6's in them. So let's stop, think, GCF. What? Stop, think, greatest common factor. Is there a greatest common factor hiding in each of these terms that I can factor out in a reverse distributed property problem and make a factorization in fully factored form so I can set each individual factor equal to 0 and solve, which is what we want to do. So let's go ahead and do that. I'll pull out a 6. We'll pull out a 2x minus 5 binomial, and the greatest common factor that exists in each of them is 8. Is that right? And we'll pull out the 3x plus 4, the greatest common Is 3, yes, yes. Leaves me with, oh boy. I've taken a 6 out, so I still have 3 remaining in the first term. And I've had 3x plus 4. Factor left. Plus, and in my second factor, I still have 6 divided, so I still have 2. And I have a single 2x minus 5 factor. Is that right? Awesome. Okay, so we've done a GCF problem, right? We've done a GCF problem. That is the greatest common factor in a reverse distributed property problem. And we could still, right, we could still do a little work in this green bracket. It appears as though we can distribute my 3 through and our outside factor 2 through, combine like terms, and rewrite as a single x term in that third green bracket. So I'm going to do one more step of simplification, and then we're ready to set our y prime expression equal to 0 and solve. And that'll tell us the x values where y, my original, had horizontal tangents because its derivative y prime was equal to 0. So here we go. We've got 6, 2x minus 5 to the 8th, 3x plus 4 to the 3rd. And then here I'd have 9x plus 12 plus 4x minus 10. So we can do that in one step. 9x plus 4x is 13x. And plus 12 minus 10 is plus 2. So we do that right. If we distribute through here, we get 9x plus 12. We get 4x minus 10. And 9x plus 12 plus 4x minus 10 is 13x plus 2. How do we do? At long last, we can finally set our expression y prime, which gives us the slope of our original function y anywhere along it, equal to 0, and solve for x. This will determine the places, the x values, where my originals, right, has horizontal tangents, because that's where the slope equals 0. Let's do it. How do I solve now that I'm in fully factored form? Well, there's the fruits of our labor. We have a fully factored form, so we can solve using the zero product property. That is, if a times b times c equals 0, then we have no choice but for a to equal 0, or b to equal 0, or c to equal 0. So set each factor equal to 0 and solve separately. So 2x minus 5 could equal 0, quantity cubed, or quantity to the 8th, or whatever. 3x plus 4 could equal 0, that would reduce to 0, and lastly 13x plus 2 could equal 0. Solving each of these separately produces how many places where my original y could have horizontal tangents? 3 places, right? We'd expect to see a horizontal tangent at x equals positive 5/2, or 2.5. We'd expect to see a horizontal tangent at x equals negative 4/3. And we'd expect to see a horizontal tangent at x equals negative 2/13. Is that right? Negative 2/13. Awesome. That was a whirlwind of simplification, and yet we did it from the very first day in our 4-2, 4-3 product and quotient rules when we were doing our product rule and simplifying. So definitely an interesting connection there between our algebra, our product rule, our power rule, our chain rule, and then the derivative, right? An application of our derivative. And so I like that problem. Jake?
Probably seems like a dumb question, but so the exponents do not matter when you're solving for the zeros?
That's a great question. So if I had 2x minus 5, right, to the 8th equal to 0, would that change my x values that produce zeros? No. And so certainly, we could write this as 2x minus 5 to the 8th power, right? And then when we undo the 8th power, by taking the 8th root of both sides, the 8th root of 0 is still 0. And so I went right to that, right to the 0 of this factor. I know that that's going to produce a 0, right? So I didn't bother writing the exponents, though we could have. Other questions? All right, so did anyone verify graphically? Did anybody want to verify graphically? Not excited? We certainly could, right? We could certainly verify graphically by looking at our calculator and adjusting our window, and we'd be looking to see, right, where my curve had horizontal tangent, where it's leveled off. We could also, right, do the second trace as the calculate menu, dy dx, and enter each of these x values. The cursor should jump at the on the curve at the x value of concern, and then spit out a derivative approximation. And you probably won't get exactly 0 for these. You'll probably get things like 0.000000681, right? That's your calculator trying to tell you the dy dx, the derivative, the y prime value would be 0, right? Or negative 0.000000806. stuff like that. Awesome. In the interest of time, though, we'll go ahead and scooch on to your OTL number 8. OTL number 8 did include related rates packet numbers 1 through 7, but don't turn that in. You're going to keep that and continue working on that. I wanted to break up the related rates practice over 2 days because it was a new strategy and concept, and it takes a couple days to sink in. So once again, we're not turning in the related rates packet today. We'll be turning it in next time. Related rates will be on your test.
Like the simple or complicated ones? The intermediate ones?
Intermediate ones.
Okay.
There'll be some easy
Okay.
and some harder.
What do you define as harder? Okay.
More challenging.
Oh, wow.
That was better than my response. All right. Please make sure that multiple pages are stapled together. Your infinite canvas score is boxed nice and big on top around the nearest half point. Your heading includes first, last name, 2A, and number 8. And you're not passing in your related rates packet today. We're going to keep it and finish it and then pass it in tomorrow. So here we go. Pásamelos, por favor. Thank you. Thank you. Are we good? Awesome. So today you're going to have an opportunity to work and review with a classmate. Someone has also asked about determining constants A and B that would make a particular function differentiable, so we can take a look at one of those together if we have time. But first, I want to make sure that we are comfortable with the relationship between continuity and differentiability. We spent a lot of time in this unit dealing with composite functions and new derivative rules, products and quotients, and I don't want you to lose sight of the connection between continuity versus differentiability that we looked at back in day 3. So here we go. Continuity, right, and differentiability are closely related. Does continuity guarantee differentiability? Or if a function is differentiable, does that then guarantee continuity? And so go ahead and decide with your partner which of these is true, A or B, and be ready to share with the class when I'm calling you. Okay, so it's like a little victory. You know, we just got to take them as they come. That's great. All right, so go ahead and share with the class which if any of these statements are true. So which of these statements is true? Which of these statements is true? So Sophia and Tess? B is true. Raise your hand if you have B. B is true. Awesome. A is not true. Okay, so what would be a counterexample for the claim that continuity implies differentiability? Why is A not true? Paul?
Cusp doesn't have a derivative.
Absolutely. If there's a corner or kink or cusp at x equals c, the function is continuous. That is, the left-hand function value is approaching the same y coordinate as the right-hand function value, and so the overall limit exists. The function is continuous, and it equals that limit because it's filled in. Right? That's a filled-in circle, and yet the function is not differentiable at x equals c because the left-hand slope value does not match the right-hand slope value, and so that's a perfect example. We also have a vertical tangent would be a situation where the function is still continuous at x equals c and yet not differentiable, right? Not because the left-hand slope doesn't match the right-hand slope, but because the slope does not exist at a vertical tangent, the slope is undefined. And so the slope is becoming infinite from the left-hand side, the slope is becoming infinite from the right-hand side, right? And so we've got a situation where we don't have a cusp, and yet it's not differentiable because we have a vertical tangent. So each of these cases are examples where the function is continuous at x equals c, but not differentiable. However, if a function is differentiable, then it must be continuous, otherwise we wouldn't have a place to hang our tangent line, or attach our tangent line. And so B is going to be a quick way to prove continuity. What's the quickest way to prove that f of x equals cotangent x is continuous at x equals pi over 6? Well, if I can show that the function is differentiable at a particular x equals c value, then it must be continuous because differentiability guarantees continuity. So here we go. If we wanted to prove that f was continuous at x equals pi over 6, the quickest way would be to prove it's differentiable. So what would I do? Well, if I could find its derivative value at x equals pi over 6 and it exists, then that would guarantee the function is also continuous. So let's go ahead and generate an expression f prime. Good thing we memorized our rules. Go ahead and tell the class what cotangent differentiates to. What would cotangent of x differentiate to? Be ready? Allie? Nice. Thank you. And so cotangent differentiates to opposite of cosecant squared x. And now I'll try to evaluate that at my x coordinate of concern. So let's see if that equals a value. So f prime of pi over 6 is equal to negative cosecant squared of pi over 6. And the good thing we know our identities. I know cosecant is the reciprocal of sine. And so this is the same as 1 over negative, and the sine of pi over 6 squared. And the sine of pi over 6, we memorized that was first quadrant, 1/2, right? That's 1/2. And so this would equal, go gadget arm, negative 1 over, what's 1/2 squared? 1/4. That in turn would be the opposite reciprocal of 1/4 is negative 4. Does negative 4 exist? No. Yes. So since f prime exists, f is differentiable at x equals pi over 6, then f must be continuous. So our statement then, we've shown that since f prime of pi over 6 exists, then f must be continuous at x equals pi over 6 because differentiability implies continuity. Vicky?
So if it wasn't continuous, like what would happen if you try to pass it through? Like what value would you be getting?
We get it does not exist, and that doesn't necessarily mean that it's not continuous, it just means it's not differentiable. Such would be the case had this been the tangent function and we were evaluating at pi over 2. Then we would have gotten a does not exist for my first derivative, right? In the case of tangent, not only would that mean the function is not differentiable, but we know that tangent has what feature at x equals pi over 2? A vertical asymptote, so it would not be continuous. However, oftentimes, particularly when dealing with rational power functions, right, that have those cusps or those root functions, odd roots, like the cube root function has the serpentine s, but it's sideways, we would get an undefined derivative at x equals c, right? And yet the function is still continuous. And so just because something's not differentiable doesn't mean it's not continuous. But if something is differentiable, then it means that it has to be continuous. Jake?
So then, if we can't find if it's differentiable, do we take the limit of the given function?
For continuity, you take the limit of the left-hand side, yep, the left-hand limit of function values, no derivative,
Yeah.
and the right-hand limit of the function values, no derivative, and set them equal to each other. Yep, and see if they're the same. Absolutely. Great. Okay. So we're going to go ahead and take a look at more complicated. Some of you are asking, what are the related rates questions? What's kind of ballpark for the test? I would say that you would have a range of questions. And so certainly I want to allow for opportunities for success. You'll have some easier ones that are straightforward, and then you might have some more complicated ones. For today's in-class example, let's take a look at the first example from our packet. Okay, so this one was a rocket question. Michaela?
Are we going to have to remember, the volume of a Collins equation?
That's a great question.
Does it have a great answer?
I'll just check. I think I provide for you, unless it's a bonus question. There might be a bonus question where I don't give you a formula.
Okay.
See what I'm saying?
Mm-hmm.
Okay, so this is not in your notes sheet, it's on your packet. Let's go ahead and take a look at a rocket. A rocket that's rising vertically at 880 feet per second when it's 4,000 feet up, and the rocket takes off 3,000 feet from the camera. How fast must the camera's elevation angle change at that instant to keep the rocket in sight? Okay, so we're going to go ahead and do our kind of step 1 and step 2 from our related rates problem solving strategy together. So we're thinking about drawing a picture, labeling those changing quantities with relevant variables, writing down our known rate and our unknown rate based on the variables that we picked. So I'll go ahead and draw a picture here. And I apologize in advance, I'm not the best drawer necessarily. But if we have a rocket and the rocket is rising vertically,
Beautiful.
and we've got a camera. And the camera has an elevation angle because I'm trying to keep that rocket in sight. And we've got maybe a vertical distance that we'll call y above the ground, and a horizontal distance from the camera to the takeoff site. Do we need to label that with an X? No, because that doesn't change. So we can label this with a constant. That's nice. So what distance separates the camera from takeoff point?
3,000.
3,000 feet. Let's go ahead and label that in. That'll be helpful. So 3,000 feet. And we now have to write down our known rates and what we're trying to find. So we want to write down our known rates, or just rate, and what we're trying to find based on the variables that we've chosen in our picture. Okay, so based on our picture, right, what are our known rates then? What are our known rates with Leibniz notation, right? Riley?
We know dy dt
And what does dy dt equal?
880 feet.
Awesome. So dy dt equals 880 feet per second. So that's the rocket rising at a rate of 880 feet per second. And what are we trying to find, right, based on our picture? So what are we trying to find based on our picture? Paul?
d theta over dt.
Ooh, so we need a theta in this picture, don't we? So we need a theta down here for the angle of elevation. Recall, the angle of elevation or angle of declination are still measured from the horizontal. It's just the angle that separates the horizontal from the line of sight up to an object in the case of elevation, or down to an object in the case of depression. So here we go. Up to an object, that would be angle theta, right, of elevation. Great. Going really fast now. All right, so we're going to try to find d theta dt at the instant when, what?
Y equals 4,000 feet.
So y equals 4,000 feet? Okay. All right, I think we have enough. So step 3 is my favorite step. Go ahead and take a look at our related rate strategy. What's our step 3 from our related rate strategy? What do we have to do then? Evie?
To get a formula.
Good. We've got to write a formula that relates our variables in our rates, our known rates in the question. So what formula relates y and theta? And I hope we have one. Is this going to be an a squared plus b squared problem? No, Jake?
Theta equals the tangent inverse of y over 3,000.
Nice. And so it looks like theta is the angle whose value of tangent is opposite over adjacent is y over 3,000. I like that, right? I like that. What if we didn't recognize that? If we didn't recognize that, we could have done our regular trig function, tangent of theta equals, okay? So Jake, I like yours even better. I just want to make sure that we have this for our notes too. I think most people would recognize that the value of tangent is y over 3,000, which then will lead directly to our inverse tangent. Awesome. Okay, so we've got our function, right, based on our variables in the question. Now what can we do? Well, we can differentiate both sides with respect to time. In doing so, we're going to generate our rates. But first, I want to make sure that we can. Does that 3,000 change at all? Then we're okay. Let's go ahead and differentiate both sides with respect to time, and then I want to go back and do it Jake's way and see if it's easier. It might be quicker. Okay. So what's the derivative of tangent of theta with respect to time? Well, I have to use the chain rule. This will be secant squared of theta, the derivative of the trig function with the angle, then times the derivative of the angle. What's the derivative of the angle? D theta dt. Thank you. Good job, because we needed that, right? We needed that rate involved. Equals, and then on the right-hand side, I have the derivative of y over 3,000. Well, recall that 3,000 is just a constant, and that's really 1/3,000th. And so the derivative of y over 3,000 is just the constant 1 over 3,000. 1 over 3,000 times the derivative of y. What's the derivative of y with respect to time? dy dt. Awesome. So we've generated an expression that includes both our known rates and our unknown rates. So I'm feeling pretty good about that. And which we were trying to solve for? We were trying to solve for this d theta dt. So let's go ahead and solve for my d theta dt. So d theta dt will be given by dy dt. I'm going to kick the 3,000 on down to the bottom. And secant squared theta would be on the bottom as well, because we're dividing over to undo the multiplication. Did we successfully isolate d theta dt? Yes? Goodness. Okay. So after I've isolated our unknown rate, Evie?
Are we able to move, instead of doing secant squared on the bottom, can we put cosine squared on the top?
Evie's idea is moving that. Instead of writing secant squared theta on the bottom, she'd like to write what on top?
Cosine squared.
Cosine squared theta. Can we do that? Yeah, the reciprocal of secant is cosine squared, and I think that would be a great idea. So let's go ahead and leave my dy dt on top. It's going to be easier for us to evaluate a cosine than it is a secant, because that's one of our big three trig functions, sine, cosine, tangent. I agree. I think that's a great idea. Let's rewrite cosine squared theta on top. That is secant squared theta on the bottom, and I still have a 3,000. All right. That's a great idea. Are we ready to evaluate? I think we are. I want to know the rate of change in my angle of elevation, that is the d theta dt that we've systematically isolated, at the instant when y equals 4,000 feet. When y equals 4,000 feet, I'll be using that information to determine the value of cosine, right? Cosine here, which I don't have. dy dt I do have. So let's go ahead and substitute. Here we go. What is dy dt at the instant when the rocket is 4,000 feet above the ground? Well, it's still the 880. I think I want to do this down here. And what's the value of cosine of theta at the instant when the rocket is 4,000 feet above? Well, that we have to figure out. What ratio is cosine? Cosine of theta is what ratio? Adjacent over hypotenuse. In our situation, that is 3,000 over whatever my hypotenuse is. Right? Well, the hypotenuse is changing. But at the instant when the height of the rocket is 4,000 feet, right, what must the hypotenuse be? 3,000, 4,000, 5,000 at the instant. And so I'm just going to write this right here for a minute, and I'm not going to leave it there. At the instant when y is 4,000, then the hypotenuse is 5,000. I'm going to take these off to export the PDF because I don't want you to think we can label the hypotenuse with a constant because it's changing. So that's 5,000. So adjacent over hypotenuse is cosine. So what fraction would represent cosine of theta? 3/5. Yeah! Good job, you guys. You're pretty awesome. No, you're pretty awesome. All over 3,000. How do we do? All right, now I'm going to take the 5,000 and I'm going to move it to right. I'm going to move it to right here, and I'm going to call that Z. So now I'm thinking math frac might be our a great strategy at any time. Let's go ahead and do math frac. We will have the related rates questions on the calculator lab portion of the test. We know that would be 9/25ths, and we could do some simplifying, but I think that in the interest of time, we could math frac it as well. Watch your order of operations, guys, if you're going to do it on the calculator. So I'm getting 0.1056, and that's 66/625ths. But I'm wondering what label would be appropriate for d theta dt, the rate of change in theta, the angle of elevation with respect to time. And here I want to make an important distinction. In AP calculus, right, we're always working in what degree measure, what angle measurement system? Radians, right? Radians are used because they provide an explicit relation between distance and angular measure, okay? Whereas a degree doesn't have any connection between distance, a radian does, and that allows us to use our side lengths here in my triangle when dealing with the rate of change in my angle. And so this must be written in radians per second. Awesome. That's a sweet problem. Okay, let's do some quick mental checks. Is the rate of change in my angle of elevation positive or negative? Positive. Does that match the problem situation? Yes, because that angle would be increasing to keep the rocket in my sight. So that's the first check. Is that a large value or a small value? A fairly small value, and yet, does that seem reasonable? I think it's okay to be small because you're 3,000 feet away from it, and it's 4,000 feet above the ground, and so I'm thinking that, right, you wouldn't have to be going too fast in your experience as you work to keep an airplane in your line of sight, right? You don't have to move your head really quickly. You're not whipping your head back and forth the way you are as the subway train passes, right, in the underground. And so we've got a situation where that object is far away from you, so you're going to change your line of sight at a smaller rate. That's awesome. Great. Okay, so what's going on? Well, we'll go ahead and do our closure, and then we'll take a look at a piecewise defined function. Again, to go ahead and make sure we're fresh with that. When f has a horizontal tangent, what must be true about f prime of x? Don't say it out loud. I'll call on you. Which of the following statements are true? And there's 3 and 4. I just put on separate pages. And so we've also got a 3 and a 4. What's the quickest way to prove continuity? At a point given a function rule, and then a function is not differentiable at x equals c if any of the following are true. And we're going to share each example. not the equal. The whole cosine, yes, the whole cosine of theta equals.
Okay, so I'm trying to figure this one out, the inverse, so it would be 1 over 1 plus the inverse. I got that part, but then the difference of the inverse would be 1 big.
Right.
Yeah.
Okay, ladies and gentlemen, let's go ahead and share our responses. Please be ready to share with the class when I call on you. Number 1 from closure, everybody get ready. When f has a horizontal tangent, what must be true about f prime of x? Paige? It must equal 0, that's true. So if f has a horizontal tangent, then f prime of x must equal 0. Absolutely. Raise your hand if you had the same. So f prime of x must equal 0 where f has horizontal tangents. Thank you. Which statement is true? Does continuity guarantee differentiability, or does differentiability guarantee continuity? Emily? B is true. Differentiability proves continuity. So the quickest way then to prove continuity is to if you're given a function rule, right? What would be the quickest way then to prove continuity if you're given a function rule, right? A function equation. Nikki? Yeah, we could find the derivative value at a point. If the derivative value exists at the point, then the function must be continuous at the point. I'll say if the derivative exists. Then f must be continuous. Awesome. And lastly, a function is not differentiable at x equals c if any of the following are true. And so we've got lots of things here. So what's one thing that would make a function not differentiable? So what would be one problem for a function to not be differentiable? Michaela?
It is not continuous.
Yeah, if my function's not continuous, then the function's not differentiable for sure. So if there's a discontinuity, and under my discontinuities, we've got 3 things, right? So any type of discontinuity. What kind of discontinuities do we have? Well, we've got our infinite discontinuity is a vertical asymptote. And so if we had a vertical asymptote at x equals c, then the function would not be differentiable at x equals c. If we had a step or jump discontinuity, and lastly, if we had a removable discontinuity, here the left-hand slope matches the right-hand slope, but the function is not defined to be that, all right, that y value in between. There's no place to hang the tangent line, right? We couldn't attach the tangent line to a point of tangency, so it's not differentiable. All right, aside from discontinuity, there's still some things that could cause problems, right? Paul referred to one earlier, right? So what's another thing that would cause a function to be not differentiable? Sophia? A cusp, right? If we had a cusp, a corner, or a kink, in general, that's an abrupt change in direction, where the left-hand slope does not match the right-hand slope. If the left-hand slope doesn't match the right-hand slope, then the overall slope does not exist, and the overall slope is the derivative. And so the derivative would not exist at x equals c if the left-hand slope does not match the right-hand slope. But there's still one other thing, right? What else is out there that would cause a function to not be differentiable? And yet no cusp. Sophia?
Is it the vertical?
It is a vertical tangent. So a vertical tangent, my derivative is undefined because of vertical slope, right? The vertical tangent has an undefined slope. So vertical tangent Whoa. crazy. Awesome. What questions do you guys have about our closure today? Okay, so let's go ahead and take a look at a piecewise defined function. That's for printables. But first I want to make sure that we understand our assignment. So our AP calculus related rates, 1 through 7 was asked last time, 7, right? And we're not collecting it, and so 8 through 13 if you haven't done it, or 7 through 13 if you haven't done it, but we will be collecting it next time. So I want you to keep that packet, you're going to continue working on it, and I want you to know as the numbers progress, it gets more complex. And so everybody 1 through 6 should be go-to problems. So it should be easy for you to complete in a test or quiz situation. Now 7 through 13 get a little bit trickier. I want you to know that numbers like 12 and 13 are kind of stretchers. They might be above and beyond what you'd be kind of expected to do in a testing situation, but I don't want to shortchange your education by not including that challenge to you and to everybody. And so once again, you're like numbers 11, 12, 13 are a little bit trickier, okay? And so now we're increasing the complexity. The concept and skill guide includes booklet problems, and I've taken the liberty of getting an answer key for everybody. So you should have picked up an answer key already. That way you don't have to worry about sifting through the Moodle and rotate counterclockwise twice to get it back so that you can read it. That's so annoying. And so you've got your own answer key. Rotate, I know, because it's always the one where you have to go 3 times around to get it back to it. You can't just do one. Yeah, turn the laptop on the side and balance it on. And then once again, your test is on Monday, next class, and so you want to make sure you're ready for that. Again, it's 2 parts, so come ready to rock and roll. I'll go ahead and pause the recording. We'll see if we can't take a look at our piecewise defined function and finding constants of A and B that make it true. But I want you to know that our stamp check will include Bellwork and activity stamps. So we got a Bellwork out of 8, and I wrote it down on the side. So I will go ahead and turn this off in a minute. So 8 and 16 for a total of 24 is what I'm finding, and I'll pull that over in just a little bit. But for now, I'll go ahead and stop the recording and see if I can't pull up a piecewise. And for our piecewise defined function, what we're going to do is find values of A and B, which will make the function differentiable at x equals 6. And so here we've got a piecewise defined function, right? We've got a breaking point here at x equals 6 where my function rule switches. On the left-hand side, it appears as though my function is given by x squared, and on the right-hand side of 6, it appears as it's given by ax plus b for constants a and b. Let's go ahead and find values of a and b, which will make this function differentiable. So we need 2 things for differentiability. Our first requirement is continuity. If we don't have continuity, right, then we might not have a place to hang our tangent line, right? And so we need to first show continuity. And continuity of my original function exists when I have the overall limit of my function as x approaches 6 is equal to the value of my function f of 6. And so let's go ahead and consider continuity as my first requirement. In order for a function to be continuous, right, the overall limit as x approaches 6 of f of x must be equal to the value of the function at x equals 6. All right, so let's go ahead and do a quick check. F of 6, I can easily find by doing which definition? Well, it looks like my function gives the value of f of 6 at the second definition because of the or equal to. And so f of 6 must equal what? 6a plus b. Good. The overall limit of my function as f approaches x requires 2 parts. The left-hand limit of my function values must equal the right-hand limit of my function values as x approaches 6. So for my left-hand side, I have to do 2 checks. I need my left-hand limit and I need my right-hand limit. Okay, which function definition will I use as x approaches 6 from the left-hand side? Sam?
X squared.
We use that top definition, x squared. And so the left-hand limit is the limit as x approaches 6 from the left of x squared. Any x value of concern in my domain of the expression? Certainly, and I can evaluate my limit from direct substitution. So I get what? 36. The right-hand limit is given by the value of the function, right? As x approaches 6 from the right-hand side, that would be the bottom definition, and I feel like we've been here before, like deja vu. I feel like we've been here before, like deja vu. I feel like we've been, because we've already evaluated the function, right, at x equals 6, and so this will be given by the right-hand side. And 6 is in the domain of the expression ax plus b, so I can evaluate the right-hand limit through direct substitution, and I get 6a plus b. So, for the overall function to be continuous, I need the left-hand limit to equal the right-hand limit, so that the overall limit exists and is equal to the value of the function, 6a plus b, which happens to be the right-hand limit. So basically, I've generated one constraint from this. I know that 6a plus b must equal 36, otherwise the overall limit would not exist. So first requirement, continuity, left-hand limit must equal the right-hand limit. That gives us one constraint. Yes? Okay. Second requirement, differentiability. We need the left-hand slope to equal the right-hand slope. This will generate a second equation, or a second constraint. So here we go. What's my left-hand slope? Well, let's see. The left-hand slope is a derivative. It's the derivative of my left-hand function definition. So my left-hand slope would be the limit as x approaches 6 from the left-hand side of f prime of x. That would be the limit as x approaches 6 from the left of f prime of x. First definition would be what? 2x. So the limit of f prime of x as x approaches 6 from the left would be 2x. Is 6 in the domain of my expression? Yes, so I can evaluate that left-hand slope value through direct substitution, and it equals, awesome, right-hand slope. That is the limit as x approaches 6 from the right-hand side of f prime of x equals, and I'll use which definition as x approaches 6 from the right? Top or bottom? Bottom, but I want f prime, not f, so what will I have to do to f's bottom definition? Differentiate it, keeping in mind that a and b are constants. So what's the derivative of ax plus b with respect to x? A, what happens to b? It's just a constant. So this is the derivative of y equals mx plus b is m. The derivative of ax plus b is a. Is 6 in the domain of a constant a? Yes. What value of this limit, no matter what x approaches a, because the limit of a constant is the constant regardless of what x is approaching. Therefore, the second constraint is basically left-hand limit equals right-hand limit creates one constraint. Left-hand slope equals right-hand slope equals a second constraint, and that gives you a system of equations that can then be solved. Oftentimes you'll have two variables here, right? If you have two variables here, but you can then solve using substitution or elimination or linear combination, right? Whatever you call it when you're in advanced algebra. In any case, this one looks like we're ready to go. A is 12, so I can, through substitution, evaluate in top 6a would be 6 times 12 is 60, 72, plus b equals 36. Subtracting over 72 from both sides produces negative 36. And so my values of A and B are, what, 12 and 36? Sorry, negative 36. Thank you, Jake. Good. Awesome. Okay, so regardless of what the values of A and B in this problem were or my original equations, our strategy is the same. Left-hand limit equals right-hand limit. That produces one constraint. Left-hand slope equals right-hand slope. That produces the second constraint. And then you solve the system of equations to generate values of A and B to satisfy the original. Is that helpful?
Yeah, so you do the same thing even if there's like, if A is in the left, like the top equation and B is in the bottom?
Yes.
It works the same.
Absolutely. You just might have to subtract over the A to generate an equation that just has A solved for and then plug it into the original.
Okay.
Absolutely.
Yeah.
Or you might have to do elimination or substitution to solve.
You should always end up with one of them equaling.
No, we could have, what if we had had A plus B equals 12? New problem. What if we had A plus B equals 12 in the second one? Same top. Would we been stuck? No, we could just subtract over the B and get 12 minus B for A, and then plug back into for A and get
Okay.
12 minus B, and then plus, you'd have two, you know what I'm saying, you'd have
So either way, you
substitution.
just have to make one of them, you have to get like an A equals or a B equals.
Yes, and then substitute the other one, or if you prefer elimination, make opposite coefficients and add them straight down, like you did solving systems in advanced algebra a long time ago. All right, we're gonna go ahead and save the recording now. Okay, great work. So let's go back to the stamp slides, so you can see exactly